Okay, so for today's talk, I'm going to be giving you the essential guides to the James Webb Space Telescope. Now, I'm hoping it's going to be about an hour. There's an awful lot to get through, so you're probably going to have more questions at the end, and I'll do my best to answer them. So when I do my talks, if it's a general question, I like to keep those to the end, but if I'm doing something and you haven't quite understood it, then raise a hand and I'll address it as we go, because it helps break it up. Otherwise it's an hour of me just rabbiting on, right? So it makes it a little bit different. So for those of you who've never been to Astro Camp before, so I am Jenny. I've been coming here for, well, since the first one. I've missed a couple for various degree related things, but I've been around for most of them. Now on the organising committee. I did my undergraduate and my PhD at Cardiff University, where I studied the stuff between the stars, so how the gas and dust content of galaxies changes over cosmic history. But while I was doing my PhD, I kind of understand that while doing science is great, I actually love talking about science even more. And so this is where I am now. I sort of do science communication as my job. I am the managing editor for an app called Sky Guide, which is available to download free on the App Store. There we go, that's my official spiel. I do a little bit of work for the BBC, so I'm one of their registered space experts for the radio, and I'm on Weatherman Walking, this series, so that's airing on Fridays, 7:30 on BBC One Wales, and it's also on BBC iPlayer. But other than doing astronomy related stuff, I like to cross stitch, and I'm owned by a cat, because I think if anyone knows, if you've got a cat, you don't own them, they own you. So for the goals of this lecture, we're going to do sort of a brief overview of the James Webb Space Telescope, why it's an infrared telescope, that deployment sequence, which is now so iconic and had never been done before. We'll have a little look at the instruments as well, and then we'll finish with covering what's been planned for its first year of science. So the James Webb Space Telescope is our next generation flagship telescope, and it's always kind of punted around as being NASA's, but actually it's a joint venture between NASA, ESA, so that's the European Space Agency, and CSA, which is the Canadian Space Agency. It's named after James Webb, who was the NASA administrator just before Apollo was, really kicking off, but the less said about him, the better, quite frankly. And the James Webb Space Telescope is a successor to Hubble. It's not a replacement. It's designed to work side by side with Hubble, who's been staring at the skies for over 30 years now. And unlike Hubble, this telescope is looking in the infrared, so it's looking at light that we can't see with our eyes. And it's got loads of different science goals. It's going to touch almost every single branch of astrophysics, but its main science goals are to try and find the first stars and the first galaxies, and then help us understand the atmospheres of potentially habitable exoplanets. So it's got some really lofty goals, and so far everything's going swimmingly, so it should be great. It is one of the most unique telescopes that has ever been launched into space, because it is so big that we physically didn't have a rocket big enough to carry it in its sort of fully formed operational state, which you can see in the centre there. And so we had to fold it up, literally origami style. We had to fold up that sun shield, put it into pallets, fold them up. We had to put up the secondary mirror, which is on those three struts in the middle. And we also even had to fold in the wings of its primary mirror. And then once it had launched, all of this had to sort of be reverse engineered. Hundreds of processes with no fail-safes, it either worked or it didn't. And there was no two ways about it. It's got a 5-layer sun shield, which helps keep the telescope cool. There's that silvery bit at the bottom there, that kind of diamond shape. And it's got a bunch of different instruments on it. So some of them are imagers, some of them are for spectroscopy, and they look at different parts of the infrared spectrum. But a good place to start when we're learning about the James Webb Space Telescope is kind of comparing it to Hubble. Hubble's a telescope that we're all very, very familiar with. And by and large, they are both similar types of telescopes in the sense of they are Cassegrain type telescopes. So that means the light comes in. So the light comes into Hubble through its aperture, goes down to a primary mirror, which is down by where those solar panels are. It bounces up to a secondary mirror, which is sort of hidden within the silver tube of Hubble. And then that light is then directed through a hole in the primary down to the instruments, which are at the back. And some of you have probably got these Cassegrain telescopes with you. I've got one. And the James Webb is very similar. So the light is collected by that hexagonal gold mirror. It's then directed to that secondary mirror, which is on those 3 struts. And then the light is directed through that black box in the middle, and then all the instruments are hidden behind there. So that's where they're similar, and that is about where their similarities end. So Hubble is primarily an optical telescope. So it sees the same light that we see with our eyes. It does a little bit of ultraviolet, a little bit of infrared, but by and large, it sees the same light that we see with our eyes. Now, the James Webb Space Telescope, on the other hand, sees almost exclusively in the infrared. It does have a little bit of capability at the red end of the visible spectrum, but by and large, it is an infrared telescope. And it does a little bit of overlap with Spitzer. So Spitzer was a kind of mid-infrared telescope, and the James Webb does mostly near-infrared, creeps over into a little bit of coverage with Spitzer, and you'll see that the comparison with Spitzer will become quite useful later on. And in the infrared, we're looking at longer wavelengths, and that means we're looking at lower energy sources, cooler things, less energetic, and it gives us access to a completely different part of the universe. So why is the James Webb Space Telescope looking in the infrared? One of the reasons is because of something called cosmological redshift. So we live in a very strange universe. We live in an expanding universe. And that means that as light is travelling through the universe, it is not immune to this stretching. And the light from the most distant parts of the universe has actually been redshifted out of our line of sight. That starlight has gone from the optical and it's now deep in the infrared. So light travels at a finite speed. So just like it takes time for us to walk to the shops, it takes time for light to get through the universe to reach us. It doesn't travel instantaneously. And as light is travelling through this universe is stretching. And the light is not immune to this stretching. And so that wavelength of light, as it's travelling billions of years from the very first early stages of the universe through to get to us, its wavelength is being stretched by this expanding universe. And that wavelength of light is slowly increasing. So instead of this starlight being emitted in the optical, which we can see with our eyes, as it's travelling through this expanding universe, it gets slowly stretched. Its wavelength of light is increasing, and it shifts from that visible range down into those longer wavelengths, deep into the infrared, which is exactly where the James Webb Space Telescope can see. So to see the light from those very first stars and galaxies, although that light would have been emitted in the optical range where starlight lives, now because it's had to travel, 13 billion years to an expanding universe, it is now deep in the infrared, invisible to Hubble, but absolutely perfect for the James Webb Space Telescope. And so this is just a little diagram again, and you can see how that starlight is emitted in the optical at shorter wavelengths in that rainbow that we're all very familiar with. And then as it's travelling through that expanding universe, that wavelength of light is getting stretched, gets longer and longer, goes into the red, goes into the infrared, where the James Webb Space Telescope can see it, and that'll be the light from the very first stars and galaxies. So we're probably quite familiar with the Hubble Deep Field or the Hubble Ultra Deep Field. So the Hubble Ultra Deep Field is where they took the Hubble Space Telescope and they stared at a seemingly empty patch of sky for several days. And in it then slowly were revealed just countless galaxies from deep in the early part of the universe. And this is what the Hubble Ultra Deep Field looks like. Now the James Webb Space Telescope is going to do a similar thing, but it is going to see so much more. And all of these galaxies that Webb is going to see, they are hidden from Hubble because their light is now deep in the infrared. But it is exactly where Webb can see it. And these are going to be the really exciting galaxies. These are the first stars, the first galaxies. We don't really understand how the first stars and galaxies formed. So when James Webb gets to see these, it's going to be very, very exciting. So the other reason we want to have a look at the universe in the infrared is the atmospheres of exoplanets. Now, most objects in space can be modelled as something called a black body, and that is they absorb all radiation that's incident upon them, and then they emit radiation then as well. The key thing about a black body is that they emit light right across the electromagnetic spectrum, so you can go from ultraviolet, visible, infrared, down into the radio. But the key point is that their peak emission wavelength, so the wavelength of light where they emit most of their radiation, is entirely dependent on temperature. It doesn't matter what it's made of, it all depends on temperature. And you can see this happening in a piece of metal. If you've ever seen a piece of metal be heated, so you start off, with your normal piece of metal. As you start heating it, it'll start glowing red hot. So we're in the red part of the visible spectrum at those longer wavelengths. It's not too hot yet. You heat that metal a little bit more. We go up into the yellow. You see it get hotter, and you can see how we're then shifting. We're getting hotter. We're going up to shorter wavelengths. So we're now in the middle of that rainbow. And then if we keep heating that metal again, we get white hot. And it just keeps going like that. And it's the same with flames. If you've ever sort of seen a Bunsen burner, you start off with like a yellowy flame, and that's slightly cooler. But then you get to the blue flame, which is hotter, and it's hotter. It's emitting that blue light because it's hotter, emitting like a black body. And as you get cooler, you drop down to lower temperatures. Most of your light is emitted at longer wavelengths. And we can see that here with these curves. So at 6,000 degrees, we're talking the temperature of the sun, and the sun appears sort of yellowy, whitish. So it's sort of emitting most of its light right in that part of the spectrum that we can see. And then as we drop down to cooler stars, we're going down, we're getting to longer and longer wavelengths. And if we keep going, we keep dropping that temperature all the way down, we get to the temperature of planets, which are about the temperature of humans, which is about 20, 30 degrees, something like that. And that peak emission is deep, deep into the infrared. And that is exactly where the James Webb Space Telescope can see. So again, this is another reason why we want to be having a look in the infrared. So one of the systems that James Webb Space Telescope is going to be having a look at is called TRAPPIST-1. It's about 40 light years away, and it's a very exciting system because it's got about 7 Earth-sized rocky planets orbiting a small red dwarf star. And all of their temperatures are about 30 degrees or so. Can I get my mouse over there? No, I can't. All of their temperatures are about 30 degrees Celsius or so. And if you remember from that previous plot, that is deep, deep into the infrared, exactly where the James Webb Space Telescope can see. And on this plot here on the right-hand side, we've got Venus and Earth just in the middle. So you can see how their temperatures compare to planet Earth, to Venus, and it's quite similar. And they'll be glowing very nice and brightly in the infrared. And of course, the best reason for studying things in the infrared is all about cosmic dust. So my favourite thing of all when it comes to space. And when we're looking in the near infrared, we can, instead of having our light obscured by all of this cosmic dust, we can instead peer through it and see what's going on behind. So this is the Monkey Head Nebula. And on the left-hand side, we have got a picture of what it looks like in the optical, so the light that we can see with our eyes. And then on the right-hand side, it's exactly the same object, but in the infrared. And this is a star-forming gas and dust cloud. And we can see that in the infrared, we can peer through all of this gas and dust. And we can see all of these newly formed stars that were previously hidden, we couldn't see before. And then if we go to longer, if we have a look again at the pillars of creation, this is again another gas and dust cloud. So this is in the Eagle Nebula, that's M16. If you want to take a look at it tonight, that's on the left-hand side. And again, in the middle picture, that's what it looks like to light that we can see with our eyes. There's all this cosmic dust, it's annoying, it's in the way, but in the infrared, we can peer straight through that. and we can see all again of these newborn stars, these recently formed stars we couldn't see before. And so it allows us to get a real handle on star formation, understanding those very early stages that would otherwise be hidden from view. And then if we go to longer infrared wavelengths, we can actually see the emission from the dust, because just like the stars, they glow brightly, so they're emitting light that we can see with our eyes. The planets are cooler, so they're emitting in the infrared. And if we keep going down again to cold cosmic dust, it will emit its light at long infrared wavelengths. And this is the constellation of Orion, so it's over there if you want to have a look at it tonight. And this is what it looks like to our eyes, you know, lovely constellation, nice nebula there, kind of gives a hint of what's going on. But then in the infrared, the whole region just comes to life. And that is this emission from this cosmic dust that's then tracing all of this gas, all of this stuff between the stars. And it's really important to have a look at this emission from this cosmic dust, because half of the starlight that has ever been created in the universe has been absorbed by this cosmic dust and then re-radiated deep in the infrared where we can't see it. So if we don't study this cosmic dust, we're literally missing out on half of the universe. So moving on from wavelengths now, onto the mirror, because I feel like this is a really obvious difference between Hubble and the James Webb Space Telescope. Now, the James Webb Space Telescope has a much, much bigger mirror, but despite that, it still has a similar resolution, so it can see a similar level of detail that Hubble can get, because normally, the bigger your mirror, the more fine details that you can pick out. But that is because the James Webb Space Telescope is looking at these longer wavelengths. And this equation up here, I've just kind of put this up for people who are interested. But the whole point with resolution, which is that symbol on the left, that's theta, the whole point of resolution is that it is proportional to the wavelength you're looking at and inversely proportional to the size of your mirror. So the bigger the mirror, the more details you can see, but the longer the wavelength, the less details you can see. And so on the screen at the bottom there, I've got this sort of level of detail the Hubble and the James Webb Space Telescope can see. They're about the same. But the key difference is with Spitzer, and we remember that's the one that we were talking about at the beginning, which was an infrared space telescope. It is an order of magnitude, you know, it is 20 times improvement over what Spitzer can see. So we're going to be able to see 20 times more detail in the infrared with the James Webb Space Telescope than we could with the sort of previous generation one. In terms of what details the James Webb Space Telescope and Hubble can be able to see, so it can see arc seconds. And arc seconds is one of these very obscure astronomy units that they like to throw in. So you have minutes, arc minutes, and arc seconds. So you have the full moon is about half a degree. And 1 degree is made up of 60 arc minutes. And then 1 arc minute is made up of 60 arc seconds. So the full moon is half a degree, which means that it's about 30 arc minutes across. And, you know, you can try and imagine looking at the moon, splitting that up into 30 segments. But a better way to think about an arc minute is if you took a football and you put 7 football pitches end to end, and you stood at one end of that and someone else held a football, that is 1 arc minute. But the James Webb Space Telescope, they can see in arc seconds the level of detail. So it's that football, 7 football pitches, it's 1/60th of that football is 1 arc second. And then the James Webb Space Telescope can see 1/10 of that. So that's the sort of level of detail that we're talking about. It's absolutely extraordinary. So another question about the James Webb Space Telescope is, why does it have this sort of segmented mirror? Because it seems a bit bizarre to sort of break your mirror up and have all of these lines across it. It doesn't seem like it's going to be very good for detecting things. We couldn't launch a solid mirror simply because it would have been far too heavy. We also couldn't fit it on any rocket. No rocket fairing was big enough, so we had to fold it. And it's hexagonal because hexagons have what's called a high filling factor. So if, you know, the ideal shape of your mirror is to be a perfect circle, but a hexagon allows you to fill that circle in with the least amount of space weighted. So that's why it's gone for the hexagon shape. And then also the hexagons allow you to sort of focus nice and easy. So we're never ever going to get that problem that we had with Hubble when it was launched and then it couldn't see anything. That's not going to happen because you can focus each of these segments and make sure that it's absolutely perfect. So this is just a picture of the James Webb Space Telescope when it was getting ready to be loaded onto the rocket fairing and stuff. And you can see how one of the wing mirrors is folded out, but the other one is folded back. So the other side would have been folded back for the launch as well. And just to kind of give you a sense of scale, just note the people at the bottom of that image, because this whole mirror is 6.5 meters across. So to achieve focus, the James Webb Space Telescope, each of these hexagonal segments can be moved. So it's got 6 actuators on the back of each of these segments, and then there's a 7th one in the middle. So the 6 allow it to sort of be tilted and turned, moved in and out and such, and then the 7th one in the middle allows you to actually bend the mirror slightly in order to get the perfect focus. And these actuators, they move really, really slowly, about the speed that a blade of grass grows at. That's how quickly they're moving. And in order to achieve perfect focus, it has to be aligned within 1/10,000th of the width of a human hair. This is how precise it has to be. It's absolutely extraordinary. So the mirrors themselves are made of a material called beryllium, and then they're coated with gold for good reflectivity for the infrared. Beryllium was chosen because it's light and it's strong. It also holds its shape across a range of temperatures, and that's really important because these mirrors are manufactured, you know, on Earth in a room which is 20 degrees or so. But the operating temperature of the James Webb Space Telescope in the infrared is about minus 230 degrees Celsius. So you can't make something and then have it, you know, bending and changing shape as it's cooling down to operating temperature. And the way they would make them is they would cut out a hexagon in the beryllium. They would then take away as much of the material as they could, so it's kind of got this crosshatch pattern to give it strength but to make it light. And then they would do this on either side of the hexagon and then cut the hexagon in half, and then that gives you 2 segments. And then of course it's polished and so on. It's then coated with just a very, very thin layer of gold. It's about 700 atoms thick, so it's only about a golf ball's worth of gold goes into the entire mirror system of the James Webb Space Telescope. And then that's done through vacuum vapor deposition. So that's where they take one of the segments, put it in a vacuum chamber, evaporate the gold, it then sticks onto the mirror in a perfectly fine layer, and that's how the coating is done. So the James Webb Space Telescope and Hubble, they are really, really far apart from each other. So Hubble operates in a low Earth orbit, a few hundred kilometres above the surface of the Earth. But the James Webb Space Telescope is way, way away from Earth. And that is because the James Webb Space Telescope is an infrared space telescope. And so it's detecting heat energy. And it can quite easily detect the heat of Earth and the heat of the moon and also the heat that's coming off of the sun. And so if it was seeing all of that, then its detectors would just be completely swamped. It wouldn't be able to see any of the heat of the universe that we're trying to detect from these stars and the galaxies and the planets and so on. And so what it needs to be is far away from the Earth and the moon. And so then it can keep the Earth and the moon and the sun at the same time behind its sun shield, blocking out that massive infrared heat source so that it can see the heat that it's actually trying to detect. And it's at a gravitationally stable point called Lagrange Point 2, which is about 1 million miles away from Earth. And I was really hoping that I could find, you know, a lovely to scale diagram, but I couldn't. So this is the best that I could find. But you can fit 30 Earths between the Earth and the moon. And the James Webb Space Telescope is, you know, 4 times that distance away. So yeah, it's really, really far away. So the Lagrange points were named after an Italian mathematician who sort of wrote down the mathematics for it, called Joseph Louis Lagrange. And they're just naturally gravitational stable points that emerge from any two-body system between the sun and the Earth or the Sun and Jupiter. Around Jupiter, at the Trojan asteroids of Jupiter, they exist at the L4 and the L5 Lagrange points. And what's special about L2 is that because you get an extra gravitational kick from the Earth, anything placed at L2 is co-orbital with Earth. So that is, it takes the same amount of time to orbit the Sun as Earth. So we can always be in communication with the James Webb Space Telescope. When it's at L2, it doesn't sit at this gravitational stable point. It does this large halo orbit, and this orbit takes about 6 months or so to complete. And that's because if it sat exactly at the L2 point, then we would have the Earth eclipsing the Sun all the time, and the telescope is solar powered, and you would just be cutting out the telescope's power all the time. So that's why when it's at this Lagrange point, it does this nice, stable, little circular orbit so that it can block out the heat of the Earth and the Sun using its sun shield, but it can still maintain its power. And one question that I was asked when I've been talking about the James Webb Space Telescope before is, if L2 is a gravitationally stable point, then what about asteroids gathering there? Because that's not going to be any good if you've got all of these asteroids, you know, sitting at the same point as where you're putting a multi-billion-dollar telescope. You don't want it getting dinged. And you can think about the L2 point, because although it's stable, it's not completely stable. You can think about the L2 gravitational point a bit like a saddle. So if you place a pebble exactly in the right position on a saddle, then it'll stay there. But give it the tiniest nudge and that's it, it'll fall off. So if asteroids ever kind of make their way to L2, they only need the tiniest gravitational nudge from another asteroid, the moon, something like that, and they'll fall away from that gravitational point. And that's why the telescope as well has these boosters to keep itself in that halo orbit, because although it's pretty stable, it's not perfect. So we've discussed the advantage of thermal isolation, so that is where it can block out the heat of the Earth and the moon and the Sun all at the same time. Because it's a reasonably stable gravitational point, it doesn't take too much fuel to keep it in its orbit. And of course, while you're there, you've got your back to the Sun, you've got your back to the Earth and the moon. You can see half of the night sky essentially at one time. So it's, you know, a really nice field of view that's open to you. And like I mentioned before, you're always in constant contact because that gravitational point is co-orbital with Earth. So you can always be speaking to the telescope. Big disadvantage of L2 is if something goes wrong, you ain't going out there to fix it. It is so far away, you know, it's 4 times further than we've ever sent any humans. So if something was to go wrong, that was it. It's not like with Hubble being in low Earth orbit, we could go and fix it. And also at the minute, we have no option to go and refuel the telescope. So once it runs out of its fuel to keep itself in that orbit, well, that's it. It's kind of abandoned out there. Although there are rumours that there are plans afoot to change this, but it's all very kind of hush-hush with NASA at the minute. But they are kind of planning to change that. So we sort of now understand the basics of the James Webb Space Telescope. And yes. Yes, very good question. So initially at launch, it was 10 years, but as I'm going to come on to in a second, the launch was so perfect that it had to use only a little bit of fuel to actually get to L2. And that means they think there's about 20 years of fuel left on board. Yeah, so it's kind of doubled its lifespan, but we don't know the full extent of the lifespan until they've done all of the calibrations and everything, and it's been in its orbit for a little while, and they have got some information about how much it's using. But yeah, best estimates at the minute are about 20 years. So launch for the James Webb Space Telescope was on an Ariane 5 from the ESA spaceport in Kourou, which is in French Guiana, so that's South America. And on an Ariane 5, because it is the most reliable and successful launch vehicle to date, and when this thing is $10 billion, that's what you want to be using. And the launch was absolutely perfect. There's no other way to do it. So on this table here that's just popped up at the bottom, you've got on the 3 columns which are to the right, you've got the ideal launch parameters for its distance and its inclination of its orbit and so on and so on. those are the ideal values, the second green column, and then the min and the max is kind of the acceptable range. And if you compare the second green column to the first green column, which are the actual launch parameters, you can see that they were almost perfection. It just could not have been any better. And of course, that means it's got more fuel, and so it can hopefully have a very long operational span. So once we've launched the telescope, it's not a case of putting it up there, switching everything on, good to go. We've actually got to unfold this thing from its launch configuration. And that began about 3 days post-launch. And this is this enormous sun shield. So I just want to point out in the bottom left-hand corner, there is a tiny little person wearing a white suit. He stood on the step ladder there. So this kind of gives you an idea of the scale of this sun shield. It's about the size of a tennis court, so it's 22 metres long, 14 metres wide at its widest point. And because the telescope is an infrared space telescope, it's looking at the heat of the universe, itself needs to be cooled down because otherwise it would only detect its own heat. And that's the point of this sun shield. And it will passively cool, so that is just by being there, it will reflect away heat and allow the telescope to cool down to its operational temperature of minus 230 degrees Celsius. So the sun shield itself is made of a material called Kapton, which you'll be very familiar with because it's the thing that made the Apollo landers gold. It's the same material there, it's been used by NASA for a very long time. And they coated the Kapton in aluminium and then they doped it with silicon. So that is, they fed silicon through the material. And that is because it gives it a high heat resistance, Kapton, and it is also, again, stable across a wide range of temperatures, which is really important because, again, manufactured at room temperature, operating at minus 230 degrees Celsius. So the silicon is really, really good at radiating away heat. That's one of the great properties of silicon. And then aluminium itself is really highly reflective. So then that encourages the infrared heat, that's coming from the sun and the earth and so on to radiate outwards, and also just the heat from the telescope as well. It encourages it all to move out. And this is why the sun shield has this unusual shape, this kind of, if you noticed, it was more bent in the middle and then it sort of got wider at the edges, and that shape is to help encourage heat go out from the center towards the edges. And the aluminium will just reflect the heat away, and it's got 5 layers, and it doesn't need 5 layers. It would work perfectly fine with 4. But the 5th layer is there as a little bit of extra redundancy if it gets hit by, micrometeoroids or something like that. And the outer layer is twice the thickness of the inner layer. And the outer layer is 0.05 millimeters thick, and then the inner ones are 0.025. So they are extraordinarily thin, but they do the job absolutely perfectly. And the layers are spaced so that we can take advantage of the vacuum, the insulating nature of vacuums. We've all got flasks with vacuums in them, and it's exactly the same sort of thing. It stops the heat propagating towards the telescope so that instead it gets trapped in between the layers, and then the aluminium and the silicon help encourage it out to the sides. One of the big problems, especially when the telescope was being constructed, is they found that the layers were tearing, and then those tears were sort of propagating right along the layers. And so what they've actually done is every sort of 6 feet or so along the individual layers of the sun shield, well, the outside one especially, they have put these little seams where they fused all the different layers of each of the 5 big layers. They've sort of fused them together, and so if it does get hit by a micrometeoroid of some kind, it will make a hole, but the hole's not going to go right across the whole sun shield. So that is a little bit of protection there to protect it against stuff like that. So the sun shield itself, after that was deployed, took a while. There was over 100 mechanisms, that sort of had to go correctly for the whole thing to be pulled out, unfolded, and then each of the layers to be tensioned. So once that had happened, the next stage then was deploying that secondary mirror. So the secondary mirror is just as important as the primary mirror, despite its name. So that primary mirror collects the light, but then it is that secondary which then directs the light to the scientific instruments. And a fun little fact is that James Webb Space Telescope's secondary mirror is about the same size as Spitzer's primary mirror. So it just kind of gives you an idea of how much more light collecting power this massive telescope is going to have to the sort of previous generation of infrared space telescopes. And then once the secondary has been deployed, those mirror wings unfolded. So that's the size of the mirror wings. There's one coming out there and then the same on the other side. And then once they'd clicked into place, each of the mirror segments were then moved from the launch configuration into where they think approximate alignment was. You know, only a few millimeters, that's all they had to move. But that took a very long time for it to happen. And then once all of this happened, it finally arrived at that L2 point. So while it's unfolding and moving mechanisms, it's traveling along to get to its final destination. And once there, we could then begin the next stage, which we're still in, which is commissioning. So this is actually getting the telescope ready to do science. And it's going to be another 3 months or so until the James Webb Space Telescope is going to be ready to do science, because we've got to align the mirror segments, which has now been done. And we then have to make sure that there's pin sharp focus for every single instrument. And I think they announced yesterday that they've done it for 3 of the 4 instruments. And the final one left to do is MIRI, which we'll come to towards the end of the talk. We'll explain what that is. And that one needs to cool down for a lot longer because it has to operate at lower temperatures. So it's not just passively cooled by that heat shield reflecting away sunlight. It's actually cooled using liquid helium, and that takes longer to sort of bring that system online and make sure that it's operating. So the James Webb Space Telescope's first focusing target was this star, which is actually a binocular target, so you can take a look at it tonight if it's clear. It's HD 84406, and with that focusing target, which is it's in Ursa Major, so it's just off the asterism of the Plough. The first thing to do was to approximately focus each segment. So you can see in the GIF in the middle, we go from each of those mirror segments giving us a picture of the star because they haven't been aligned properly yet. And you can see this is the same star, but we've just got repeated images of it. And it goes from everything being blurry to then, you know, pretty good sharp star points. And then each of those individual images of the star with, you know, one image coming from each segment, they're then moved and aligned and put together to make one focused image of the star, which is of course exactly what you want. So here we can see we've got each of the segments giving a picture of the star, and then once it's focused, each of those pictures of the stars are moved together so we get the first focus. And then it's a case of really tweaking that focus. So you want that starlight to be absolutely focused into one single point. And so they do that by moving these pictures from each of the segments in and out, tweaking the focus, moving them back in. You know, it took absolutely weeks to get this right. You're probably familiar with the resulting focusing picture, which was this one, which was released a couple of weeks ago. And this is super, super exciting. So this is a different target star that it went to do that final fine phasing of the focusing, where it was, you know, moving the individual stars in and out and then tweaking the focus, getting it to that sharp point. And this is what we end up with. So we've got the diffraction spikes. The big ones are from the struts, from the holding that secondary mirror in place, and then the smaller kind of horizontal one, that's a result of the edges of those mirror segments. But of course, James Webb Space Telescope won't be looking at anything this bright. This is just for calibrating the telescope and getting it into perfect focus. And to give you an idea of the field of view of the James Webb Space Telescope, this is that calibration image. So it's this here in the middle. this is the field of view of someone's 10-inch telescope back here on the ground. So it's, yeah, it's absolutely tiny. But oh God, wait till you see what pops up in the middle of this calibration image in a second. So to give us an idea of how much better the James Webb Space Telescope is compared to previous sort of telescopes that have looked at this star before, the one on the left this is images that were taken using 1.2 meter telescopes on the ground. And we can see the star in the center, and we can see a couple of other blobs. There's one galaxy, which is that blue circle there, which we've known about, and that crops up in the James Webb Space Telescope image as well. And then we've also got on the right another ground-based images. This was using two 1.8 meter telescopes acting as one telescope again. And you can see there's a few blobs. You've got the bright star in the middle, obviously, and then there's some other blobs in the image. But, you know, we can see in the James Webb Space Telescope, I'm hoping it's coming out in the sunlight, there are lots and lots of really sharply, finely focused blobs in the background. And again, we can see how it compares to optical versus infrared. And so we've got an optical one, optical to near infrared in the center from an old ground-based survey. And you can see that there are two blobs in that image. But in the James Webb Space Telescope, suddenly those blobs have been resolved into 4 blobs, not just 2. And you can see that there's beautiful spiral structure and all sorts of details that were completely invisible to us before. But now that we've got the James Webb Space Telescope with this bigger mirror, it can collect more photons, so it can see fainter objects. It's got the bigger mirror to see more details, so you're suddenly resolving these blobs in our old images into, you know, actual galaxies, and it's absolutely astonishing. So if we take the calibration image, and you can do this, and I highly recommend you do this. Go onto the NASA website, just download the calibration image, and then you just whack up the brightness, and then suddenly all of these objects start popping out from the background. And nearly every single blob that's in the background of this image is not a star, but a distant galaxy. And these are galaxies which we have never seen before. And this isn't even a science image. This is just the calibration image. And we've just got all of these galaxies popping up from the very distant early universe. So if you remember right at the beginning of the talk, I was talking about how that light from the stars and the galaxies is cosmologically redshifted. And that is exactly what we're seeing now. We're seeing these really early galaxies just popping up into view. And it's worth spending a little bit of time roving around this image. So down the bottom here, I'm hoping that it's coming out on the screen okay. This is a really beautiful spiral galaxy, a face-on spiral where we can see beautiful spiral arms sweeping around like this. And then to the bottom of it, that's an edge-on galaxy that we're just catching at the bottom of the image. Then at the bottom on the left, this again is another beautiful face-on spiral. This is a more flocculent type spiral galaxy. And all of these are accidents. The whole point of the calibration image was to get this star nice and pin-sharp focus. But by accident, we've literally discovered like dozens of new galaxies. So it's absolutely fascinating. In the sort of lower left middle, we've got this curious shape. And I strongly believe that this is an Einstein Cross. So this is evidence of gravitational lensing. So this is where we have a massive foreground object, which is bending the light from a background object, and it's forcing that light to bend around and magnifying it. And so those 4 images are probably the same galaxy, but just the image repeated 4 times from this gravitational lensing. And how have we got gravitational lensing in a calibration image from this telescope before it's even ready to do science? It's just absolutely bananas. And then in the sort of top left over there, we can see examples again of face-on spirals, edge-on spirals. But the really, really exciting thing is, you know, a lot of people will get really distracted by this. Again, you've got a lovely sort of edge-on spiral, and then you've got one which has got clearly some beautiful spiral arms. But the really exciting ones are these really, really faint blobs, which they are blobs even according to the James Webb Space Telescope, because these are those early galaxies that we have never ever seen before. These are the sort of ones that we're really looking for, those first stars, those first galaxies. Yeah, they're the super, super exciting ones. And it's just popping up unintentionally in these calibration images. Yes?
Since that's a calibration image,
Yeah.
can we suppose that the resolution will actually improve from that?
So with this one, this is a 35-minute exposure, I believe. So the resolution should stay about the same, but we'll be able to see more in the sense of we'll do longer exposures and be able to see, you know, fainter objects collect more of those photons. So we'll be able to see the same level of detail, but far more stuff. And of course then with other instruments as well. Talking of instruments, we should probably cover the instruments that the James Webb Space Telescope is using to create these images. So it's got a bunch of different instruments. So first of all, we have the fine guidance sensor and the near-infrared imager or slitless spectrograph. And largely this is to allow the James Webb Space Telescope to point to its target and track and stay on there. And it uses a bunch of guide stars, the same catalogue by Hubble. And it can do a little bit of science, but it's not designed to do science. But you know, if you're looking at something and there's an exoplanet, it can detect it passing in front of that star. So you can do a little bit of science with it. And the fine guidance system, you know, it works with what's known as the attitude control subsystem. So these are reaction wheels and gyroscopes and all sorts of stuff like that that the telescope will use to make sure that it's tracking the object. You know, this telescope will be staring at things for days sometimes. So it's really important to make sure that this one is working properly. Now, the first instrument to really talk about is the one that was used to take that calibration image to initially focus the telescope, and then subsequently when they're turning on the other instruments, they will be individually focused using internal mechanisms within the instrument so that we're not messing around with the mirrors too much, because now that those mirrors are good and that they're focused, we're not going to touch them unless something catastrophic happens. And so the image that was taken by NIRCam is that focusing star, and NIRCam is the primary imager, so it's doing the bulk of the pretty pictures. This is where they're going to come from. And it's again just passively cooled using that sun shield that's reflecting away the heat of the universe. And what's really exciting with NIRCam is that it can stare at two patches of sky, so you can see the two patches of sky bounded by the red boxes. It can look at those two at the same time and do two different wavelengths at the same time, and that is really novel. That's very exciting. So we can have, you know, those two patches bounded by the red, and then the blue is one set of wavelengths, and then the red is another set of wavelengths. And especially for transient phenomena, so things which are changing very rapidly, to be able to see what they're doing at two different wavelengths at exactly the same time will be transformative, rather than sort of taking a picture, waiting 10 minutes, taking another picture, because something could have happened in those 10 minutes, and now we can really catch it and do some really interesting diagnostics with it. It has lots and lots of fancy equipment attached to it. One of the things it has is something called chronographs, and these essentially you want when you're looking at very, very faint planets around, you know, bright stars. And we take a chronograph and we block out the starlight, and by blocking out that bright starlight we can then actually, you know, see the planets a lot better. So this is an example of a chronograph that's blocking out bright starlight in the centre, and those four blobs that you can see moving around are actual pictures of actual planets going around that star. And I think this is one of my favourite little videos of all time. I think it's astonishing that we can actually see planets going around other stars. So it does have a little bit of spectroscopic capability, and we'll come on to spectroscopy in just a second. And of course, it's got dozens of filters, so you can do broadband, you can do narrowband, and everything in between. So complementing NIRCam, which is the pretty pictures, we have NIRSpec. And NIRSpec is the near-infrared spectrograph. And spectroscopy is just like when you have sunlight shining through rain, shining through water droplets, and you get light from the sun split up into a rainbow. That is exactly what a spectrograph does. So you just shine your light into a spectrograph, it splits it up into its constituent parts, it splits it up into that rainbow, And this really helps us diagnose composition and the characterization of whatever we're looking at. So we might, for example, be looking at a gas nebula, and if that gaseous nebula is in front of a bright star, the elements in that gaseous nebula will absorb particular energies from that starlight at very particular wavelengths. And when we look at the spectrum, we'll have an absence of light at very, very specific wavelengths. And each molecule, element, chemical in the universe has its own set of wavelengths, like a fingerprint, essentially. And so when we identify those lines, we can then figure out exactly whatever we're looking at is made up of. Alternatively, if we're just looking at the emission from the gas itself, so the glowing gas, then we will get light appearing at very, very specific wavelengths corresponding to the composition of that gas, which is what's on the bottom left there. And the absorption spectrum is particularly exciting for exoplanet atmospheres. So if we imagine we're looking at a star and we're watching a planet pass in front of that star, a lot of that starlight, a small chunk of that starlight really, I should say, will be blocked out by that planet moving in front. But an even smaller fraction of that starlight will shine through the atmosphere of that exoplanet. And as that starlight is going through that atmosphere, the gases in the atmosphere of that exoplanet will absorb some of that light at very specific energies, very specific wavelengths. And we can compare the starlight when there's no planet passing in front of it compared to when the planet is passing in front of it, and see what's missing when that planet is there. And then by looking at those wavelengths, we can diagnose what is in that planet's atmosphere. So is there carbon dioxide? Is there methane, which is a really popular biosignature? And then, of course, temperature, pressures, they affect the signals as well. So spectroscopy is a really powerful diagnostic tool for gases, planets, but also galaxies as well, because galaxies are full of gas. And that is really interesting for understanding, star-forming gas and so on. And NearSpec has a really, really powerful tool on it called Integral Field Unit Spectroscopy, where you can imagine taking a picture. So this is a picture of a galaxy, but every single pixel in that picture is a spectrum. So you can imagine you've got your picture of your galaxy, and you can take one pixel and you can peer into that pixel, stretch that pixel's light out, and in that pixel how much oxygen there is, how much hydrogen there is, how much carbon there is. And you can do that for your entire galaxy. You can see how things are changing in the spiral arms compared to the core of a galaxy. It's a very powerful tool that NearSpec has. It's going to be really, really brilliant. Another massive innovation of NearSpec is it has something called multi-object spectroscopy. So it has, with this tool, you've got this field of view with the 4 squares. And each of these quadrants has 250,000 shutters over it. And every single shutter can be individually controlled. So they just do it by passing a current across them, and you can open them and close them. So you can imagine if you're looking at this nebula, perhaps you just want to trace one part of the filamentary structure. You can block out all of the other light and just focus on that filament. Maybe you're looking at a cluster of galaxies and you just want to get the light just from the galaxies. You want to block out the light from any interfering stars, and you can do that. And each of these shutters is about the width of a human hair. It's absolutely astonishing. Yeah, it's amazing. This is going to be absolutely transformative. Then the final instrument to mention, which is MIRI, because it's looking in the mid-infrared, it has to look at these longer infrared wavelengths. It's cooled using liquid helium down to lower temperatures than what you can just achieve with the sun shield. And it has a lot of the capabilities of the previous instruments. So it does imaging, it also does that spectroscopy, it's got the chronographs, all sorts of different things. And one of the really powerful tools of the James Webb is that you can use more than one instrument at the same time, and this means that we can pack in twice 3 times the amount of science, because the whole focal plane of the James Webb Space Telescope looks like this. So every instrument looks at a slightly different patch of nearby sky. And if you want to use NearCam to look at something, but you've got an interesting object just off to one side, then you might use MIRI to have a look at that at the same time. And then this means that you can either do your science on several objects at the same time, or if 2 people happen to be looking at objects on nearby patches of sky, you can run 2 separate science programs at the same time. So it just doubles the amount of science that this telescope can do. And the science that this telescope is going to be doing, it will literally touch almost every single branch above astrophysics. You know, we've planned everything from asteroids to the very first stars and galaxies. But the most exciting thing that James Webb will do are the things that we can't even imagine what it's going to reveal. Like when we did that calibration image and just all these background galaxies were popping up. But one big question is, how do you choose the science that it does? How do you decide who gets to use the telescope? That's a big question. And in the early days of astronomy, it was whoever built the telescope, that's who got to use it. But today, telescopes are built by thousands of people because it's just too expensive. You require too much expertise to just have one person building something like this. And so this introduces an enormous dilemma, because who does get to use it? There's only so many hours in a year. So how do you assign the time? So there's 4 different categories of observations. One of them are called the calibration programs, and these are there to test instruments, you know, establish if there are bad pixels in the detectors, have a look at objects which we understand so that we can then characterize how the telescope is performing. And those are all done by the people who built the telescope, built the instruments, and they aren't really proper science. They're just there to get the telescope online. So the people who helped build the telescope, they also get guaranteed time observations. And guaranteed time observations in the first year amount to about 3,800 hours. And 150 of those hours are dedicated to the Hubble Ultra Deep Field, which is in this patch of sky. It's near the constellation of Fornax. And they're gonna stare at the Hubble Ultra Deep Field, and of course, looking in the infrared, we are going to see some of those first early stars and galaxies. With MIRI, we're hoping to discover new galaxies with active black holes, and then of course study some of those galaxies that Hubble already knows about in a completely different part of the spectrum, having a look at all the new science and physics. So this is a zoomed in view of the Hubble Ultra Deep Field. This is Hubble's view of it, so you can imagine this is going to just be, you think this is full of galaxies, you wait until James Webb gets onto this. It's going to be filling in those little gaps that we can see with even more galaxies. There are lots and lots of exoplanet projects in the guaranteed time observations. The TRAPPIST planets that I mentioned before, people are particularly interested in trying to understand, are they habitable worlds? But then also in our solar system, we'll be having a look at the icy moons, so particularly Europa and Enceladus. We want to really try and nail down what's going on with these suspected hydrothermal vents that we think exist on these icy moons. Another category of projects are known as the Director's Discretionary Early Release Science. And this is only about 500 hours. And these are high priority exploratory projects just to kind of allow astronomers to get a handle on how to use the telescope. Because when you take an image, all of the astro imagers will be able to tell you. And you know from Justin's talk yesterday that you don't just take a picture and then you're done. You have to do all sorts of processing afterwards, and it's no different for these big space telescopes. And the data from this program is released immediately to the community, and that allows people to build their pipelines, get used to handling the James Webb Space Telescope data so that they can see what it looks like, develop their analysis software. But the big chunk, most of the time, has gone to the General Observer Programme, so that's about 6,000 hours worth. And these are projects proposed just by the worldwide astronomical community. So you don't have to have worked on James Webb, you don't have to have helped build it in order to get time on it as well. And these were chosen in a peer-reviewed dual anonymous process. So the idea is an astronomer writes a report saying, I would like to look at this object and I would like this much time and I would like to use this instrument and it's really important because XYZ. Then the names are removed and it's sent out into a panel. The panel then reviews it anonymously and it's all ranked and the best ones win, essentially. And this dual anonymous process is really, really important. First of all, on the right-hand side, when the anonymity was introduced for Hubble, we saw the number of people who had never got time on Hubble before shoot through the roof. So you can see where it began here, the last 4 columns. Scientists who, you know, their names weren't known, they weren't the big wigs in astronomy. As soon as the names were removed and it was just purely judged on the merit of the science in the proposal, then people who'd never been able to use Hubble before suddenly got time on it. And again, it's really important for ensuring equality across gender, because as soon as you remove, you don't know whether people are male or female, then the equality, again, it converges to where it should be, you know, 50-50. So it's really important to have this blind process. And competition, oh yes.
Do you know if it is 50-50 split?
We don't, it hasn't been revealed yet. So this is data from Hubble because they haven't revealed it yet for the James Webb Space Telescope. But yeah, that's a really good question. So this is all Hubble data. I imagine that that'll start coming out soon. It'll be released. But yeah, good question. So competition to get time on James Webb was really, really stiff. You only had between a 20 and 25% chance of getting time. And you've got to remember that these were all done before the telescope had even launched, before we even knew if the telescope was going to work. So now that we can see how powerful it is, you can imagine it's going to get, you know, even harder to get time on this telescope. But what are people doing? So in the General Observer Programme, a big theme is characterising the atmospheres of small rocky planets. It is that hunt for Earth 2.0, yes.
I just wondered if you'd applied.
No, well, no, I don't do active research anymore. No. But I do know people who have got time. So sort of my old colleagues and yeah, I'm watching them closely. But yes, where was I? Yeah, characterising the atmospheres of small rocky planets. So in particular around M-dwarf stars. So these are smaller than the sun. They're the most common type of star in our galaxy, but they are extremely violent. They flare. I mean, our star has been flaring recently. For us, it gives us beautiful aurora. But for planets around M-dwarf stars, we think could be disastrous for life. Just the amount of sterilising ultraviolet radiation that's emitted during these flares, and also X-rays as well. So there's a lot of time dedicated in these programmes to try and understand if these flares strip away the atmospheres from small rocky worlds and then renders them uninhabitable to life as we know it. They're over 10% of the time, so over 600 hours are dedicated to 3 deep surveys of the universe. One of them isn't in the cosmos field, which I'm really excited about because this was the field that I studied during my PhD. And this is really trying to hunt for those first stars and galaxies. And we know about 500,000 galaxies in this small patch of sky. You can see the scale of the moon for comparison. And so we're going to get more data on these galaxies that we know about, but we're also going to be discovering, we think, tens of thousands of new galaxies in this tiny patch of sky. We're going to partner up with the Event Horizon Telescope and try and image the supermassive black hole at the centre of the Milky Way. I'm super excited about this. So you'll remember this image from nearby galaxy M87, which was imaging the black hole is in the centre here. So this is the Event Horizon, a little bit bigger than the black hole, but we're going to try and get something like this, but for the centre of our galaxy. We're going to have a look at the triangulum, so M33, that's a nearby galaxy to us, one of our neighbours, and we're going to try and actually resolve individual stars in this nearby galaxy. It's going to be having a look at Mars, Jupiter, Saturn, Uranus, Neptune, also looking at the moons of these planets. It's going to be studying asteroids, comets. If we get one of those interstellar interlopers like Borisov, then it'll, you know, shut down everything else and turn straight to that. It's doing everything. So one really big question now that we know the amazing science that it's going to be doing is when can we expect the first images to come out. So it's not going to be, unfortunately, for another 3 months or so while they're focusing the other instruments, bringing everything online. They will not exactly look like Hubble images because, of course, we're looking in the infrared, we're looking in a different part of the electromagnetic spectrum, but they'll still be extremely spectacular. I mean, they will have the same level of detail that we can see in Hubble, but of course, looking at the invisible universe. But mostly, James Webb is being used for its spectroscopic capabilities, so it's really being used as an analysis tool rather than just generating pretty pictures, which we know so well for Hubble. But without a doubt, the most exciting thing of James Webb is the things that we can't plan for, which is illustrated beautifully by that calibration image, where we were just trying to look at a really bright star to get our focus correct, and then literally dozens of new galaxies were popping up in the background. And with that, that is your essential guide to the James Webb Space Telescope. So I hope you enjoyed it, and I will take questions.